Hello, today we're going to be talking about relations and functions, and more specifically, whether a relation is a function or not. So by the end of today's lesson, you should be able to look at an ordered pair, a table, a map, or a graph and say, yes, this relation is a function, or no, it's not, and tell me why. Now, you may not remember what a relation or a function is, so we're going to start today off by reviewing those definitions. So if we look at the definition of a relation, it's the mathematical term for a rule or correspondence. It's usually represented by formulas or equations. Now, that's a fancy way of just saying it's a set of numbers. So it's just one set of numbers that is somehow related to another set. It doesn't mean it's a function or not. It's just a bunch of ordered pairs or just a group of numbers that we relate to another group of numbers. Now, a function, though, is a special kind of relation, all right? And that matches each term from one set with exactly one item from a different set. You may have heard of this before when you talked about in another math class about functions, is we would say that for every x, there's exactly one y. And that's not a bad way to look at it. But as we look through specific examples, we might want to clarify our definition. Let's first take this over to some ordered pairs and see if we can define functions or not. So I like to look at functions when I first introduce it as a machine. So we've got this thing, and I call it my function machine. And over here is where we're going to input a number, and right here is where a number gets outputted. So for instance, if I have these ordered pairs right here, I input my x value right here, and then out spits the y. So the machine is our function machine. And so remember, this is our x value, this is our y value. We're going to input a -2, and out comes a 3. When we put 4 into the machine, it spits out a 6. When we put 8 into the machine, it spits out a -15. So for every x that we put in, a unique y was put out. So it's not like I put in -2 later on and a 7 came out. So that sometimes a 3 comes out and sometimes a 7 comes out. We want this thing to be predictable. Okay? So every time I put in a specific x value, a matching y unique to that x value should come out. So in this case, we say, yes, this is a function. Let's look at the next one. The next one, I input a 3, so 3 goes into the machine, and out comes a -5. Then I input another 3, goes into the machine, so it's the same input as this one right here, but this time an 8 comes out. Well, that's different than the -5 here. In order for this to be a function, it has to be a consistent output for that one x value. So 8 and -5 are not the same. We can go ahead and stop there and say, no, this relation is not a function. Okay? Now, some students, somewhere in their past, they've learned this trick where they just look for the x values in a relation to be the same. And sometimes they incorrectly say, hey, if the x values are the same, it's not a function. And that's not always the case. What we want is a unique y value for that x value. So in this case, the y values are not unique. They're different y values. Look at number 3 right here. I put a 5 into the machine up here, and what comes out? A 9 does. Okay? Put an 8 into the machine, and a 2 comes out. Put a 5 into the machine, and a 9 comes out. Now, here's where we have that repeating x value. So I'm putting another 5 into the machine. But this time, unlike the last time, I do get the same number coming out. So that's okay. So, let's look at this one last right here. The 3 goes in, the 4 comes out. That's okay as well. What I want to get at with this example is just because you have the same x value listed twice, it doesn't mean it's not a function. It's just the y value has to match up in both cases. It's not a bad strategy. A lot of students do this. I myself do this. When I'm looking at problems like this, the first thing I jump to is, do I have repeated x values? If I've got repeated x values, those y values better match up. If they don't, I can automatically say, hey, that thing's not a function. Okay? So that's a nice trick when we're looking at ordered pairs and tables and those sorts of things. Let's look at a relationship mapping here. So suppose I have this right here. This is another way we can represent relations and determine whether they're functions or not. We basically have our inputs on the left side in this bubble and then our outputs over here on this side. And these blue arrows right here represent what that output becomes. When I input these things into the machine, these are my outputs. So on this first one, I've got 0, and we say it maps to -2. So sometimes I put 0 into that function, and out pops a -2. Sometimes I put 0 into that thing. I mistakenly used the word function. I mean that function machine, where we're testing to see if it's a function or not. But I put 0 into the machine, and out pops a 1. So sometimes out comes a -2, sometimes out comes a 1. There's not a unique output for every input I've got going on there. So I can actually stop right there and say, no, this is not a function. All right, let's look at number 5 here. So number 5, I put a 3 into the machine, out comes a 6. I put an 8 into the machine, out comes a 6. I put a 4 into the machine, and once again, out comes a 6. So is this a function or not? For every input, do I only have one output? Well, yeah. For every input, every time I put in a 3, out comes a 6. Every time I put in an 8, out comes a 6. It doesn't matter if the outputs are the same. What matters is, do I have any x values or inputs that are giving me more than one answer? Okay? And so in this case, this is a function. Later on, we'll realize that this is what we call not a one-to-one function. So it doesn't have an inverse. But those are things we can talk about later, okay? Because the 6, if you switched them around, the 6 is mapping back to other numbers. But don't worry about that for now. We'll talk about it in a future lesson. So in this case, we have, yes, this is a function. Next one, number 6 right here. Input 3, it goes to 3. Input 8, it goes to 3. That's okay so far. Input a 5, it goes to 2. And when we input a -1, it goes to 4. It looks good here. Yes, this is a function. For every input, I get one output. And in general, when we're looking at it in this mapping sense to determine whether it's a function or not, we're really looking to see if we have two things coming out from a number. Okay? The only one that we had that on was the first one we did up here. And notice 0 had 2 arrows coming from it. They were going to 2 different numbers there. These numbers, by the way, when you're listing a group, they should only be represented once. So we shouldn't have -2 listed more than once or anything like that. And that kind of helps us be able to quickly visualize and say, because of this right here, it's not a function. Another way we can look at this is through tables. So let's look at a table representation of a relation and determine whether it's a function or not. This one we can kind of use just like we did with ordered pairs, and we can say, look, I've got an input of 3, out comes a 5. I got an input of 2, out comes an 8. So far we're good. I notice that here and here I have repeated inputs. So the outputs had better be the same. Okay, they are. 3 in goes 3, out goes 5. That looks good so far. -1 is new, and out comes a 4. 2 is a different repeated input. Notice I've got 2 going in here into the machine and 2 right there going into the machine. So the outputs had better be the same if it's a function. 2 goes in, 8 goes out, 2 goes in, out comes a 6. So that's not good. We're putting in 2 into the relation and it's giving us 2 different answers. It's not predictable. We're going to say, no, this is not representing a function. All right, so you can use tables, and they work a lot like ordered pairs. They're just, instead of listed in a set of parentheses, they're being listed there as, a chart. Now, another way that many of you might have remembered from previous math classes is we can represent it graphically. We can look and say, is this a function or not? Now remember, on a graph, this is our x-axis, this is our y-axis. So for every x value we could pick on the x-axis, there should only be one y value that it goes to. So for instance, right here, when x equals 1, it looks like the y value is -5 or really close to -5. So x equals 1, you get something like -5. You don't get anything else. There's no other green marking up here that tells me the function goes somewhere else. Now, you may or may not remember it, but a nice way to test it, whether a graph is a function or not, is to use what we call the vertical line test. So the vertical line test works like this. We take a vertical line and we move it across the graph. And if the vertical line, in this case, it's the edge of my ruler right here, if it intersects the graph more than once when you've got it vertical, it's not a function. So remember, when I talk in math terms about the graph, sometimes we call this Cartesian plane a graph paper. I'm actually speaking about what's drawn in green right here, the graph, or what's drawn in green over here. That's the graph, okay? I'm not actually talking about what I'm writing on. It's what function or relation that I'm drawing here. So in this case, it doesn't matter where I go. If I draw a vertical line, imagine this blue vertical line moving across the page, it only intersects the graph in one point. So from what we can tell here, this must be a function. Now look at number 9. Number 9 is an example of when we don't have a function, because if I draw a vertical line right here, notice it intersects the graph in 2 spots. Mainly so we can say that when x is 1, 2, 3, when x equals, well, this is more like 2, maybe when x equals 2.5, we'll say, the y value could be 2.5 or it could be -2.5. So in this case, we do not have a function because we're inputting 2.5 and the y output is 2 different values. So, or you could just say it does not pass the vertical line test. If I ask you on a test or a quiz, I give you a graph and say, is this a function or not? All you got to do is say yes or no. Yes, it passes the vertical line test, so it's a function, or no, it does not, so it's not. Now, these 2 bottom ones right here sometimes are a little tricky for students when they first see them. These are what we call piecewise functions. So basically, it's just combining 2 different graphs, and we're setting limits on the domains of these functions. So from, I think this is 1, 2, 3, 4, 5, 6, from -6 all the way up to +2, this is the function that we're looking at. And then from +2 to, it looks like about 6, this is the function we're dealing with. So the question here is this a piecewise function, or is it just some piecewise stuff going on here, not a function at all? So we're going to use the vertical line test and see if it intersects anywhere more than once. And I think the question that gets jumped to is right here, what's going on at x equals 2. So when x equals 2, do we have a y value at 4, or do we have a y value at -1, or do we have both? And the key is whether this dot is solid or empty. If it's empty, it's telling me that there is no y value there at -1. Okay, so basically when x equals 2 and beyond, you're following along here, and you're picking up just a little bit below -1 when you're just a little bit past just a little bit past x equals 2. So the value in this case at 2, when x equals 2, y is equal to 4, not this one down here. So this one is a yes, it does pass the vertical line test. Now, if that confused you, maybe number 11 will clear it up. You're like, if you really feel like -1 should be part of this and it shouldn't pass the vertical line test, look at when we do have an issue. So notice the difference between these here at x equals 2. In this case, both are solid. So this means when x equals 2, you've actually got 2 points going on. You've got when x is 2, y is 4, and when x is 2, y is also 0. So in this case, you have the same input 2 and 2 different outputs. Over here, when x equals 2, y equals 4, and that's it. Because this emptiness right here, whoever drew this graph is telling you there is no value in this, well, -1 is not the value here when x equals 2. All right, it's somewhere over here, -1 on the range. So anyway, that's the difference between these. This one is no, because right here is the only spot where the vertical line test does not work. See how it intersects twice there. Right here, when we put in that vertical line, it only intersects right there. That's an empty spot, okay? So hopefully that clears it up with graphing for you, and you'll get some practice in your homework assignment for that. Now, We can also test for functions algebraically. So let's look at some of those. So in order to test algebraically, what we want to do is get y by itself and see if there's more than one possible x value that makes the statement true. These come with a little bit of trial and error, so as you practice these problems, you'll start to recognize real quickly like, hey, this is a function, or no, this is not. And so for this first one right here, what I want to do is get y by itself. So I'm going to subtract x squared from both sides, and I get y is equal to 1 minus x squared. Now, let's take a look at this problem. So the question here is, can I put a value in for x that would give me two different y values? And the answer is no. It doesn't matter what I put in for x, I'm going to square it, it's going to be a unique number, and when I say 1 minus it, it's going to be a unique number. But there are other ways that we can check this, and one of them is graphically. Now, you can't use a graphing calculator on a quiz or a test, but I still think it's useful as you do your homework to graph these things and get used to seeing what these look like. So if you have x squared right here, you should remember, hey, that's what a parabola looks like. And if you don't remember that, we're going to go over parent functions very soon so that you do. And then this plus 1 will shift the graph up 1, and the negative flips that. So for instance, let's look over here at Desmos. So this is desmos.com. I encourage you to go through, create an account if you haven't already. That was in our introductory video to the course. Create an account so we can start to save these graphs. When we get to parent functions, I'm going to take you all through how to save different graphs, how to organize them, and why that's useful. But for today, we're just going to check out the graph and see why this is a function graphically. So if we just had y equals x squared, x squared like this, that's what it looks like. And if we put a negative in front of it, it flips it. And if we put plus 1 out in the front or on the end, it's going to shift it up 1. So this is what our graph looks like. And if I wanted to take a vertical line over it, let's say we had x, let's just say x equals -3 for right now. Actually, I'm going to make it a slider. Let's see if we can do that. Where is it? Let's see if we have one x. No. Anyway, give me just a moment. I'll figure out how to get a slider on here. Okay, usually when I put a slider in on something like this, I can just do like x equals a, and it asks me to use like, hey, do you want to make a slider? It's not doing that here. And so what I did, and there might be an easier way to do it, but I just kind of tricked it by making it think I was doing something in y equals mx plus b. So y equals ax. And there it is, add a slider. So I'm going to add a slider. I'm going to get rid of this x, I'm going to get rid of this y, and put the x there. And so remember, when x equals 5, that's a vertical line at 5. When x equals 3, that's a vertical line at 3, and so forth. What I want to do is I'm basically telling Desmos that x equals a, where a is a variable. And down below, they add a slider where I can slide the value. And this allows me to slide a vertical line across from it. And it allows us to see the vertical line test done on our function here. And notice there's nowhere a vertical line will intersect the graph more than once. So going back to our original question, yes, this right here is a function. Now before we go trying to graph this one, let's ask ourselves, is it a function or not? And so, like I said before, get y by itself. So I'm going to add x squared to both sides. So y equals x squared plus 1. And then I'm going to take the square root of both sides. So y equals the square root of x squared plus 1. Now, I introduced the square root here. So remember from the previous lesson, when we introduce the square root, we have to put a plus or minus in front of it. So in this case, let's try a value for, like, say, when x equals 3. If x equals 3, we get, let's see, you put 3 in here, we get 9 plus 1, which is 10. So we get the positive root of 10 and the negative root of 10. The positive root of 10 and the negative root of 10. Remember what that plus or minus means. You've got two different answers going on. So in this case, no matter what value I put in for x, I'm going to get the positive root and the negative root. I'm getting two different values. So my answer here is no, it's not a function. let's take a look and see what that graph right there looks like. So I'm going to come back up here and let's type that back in. We're going to say, let's see, what was the equation? Negative x squared. And if you don't know how to put in the square key, if you hit Shift 6, that's where the square key is, or the caret key, and then you can put in 2 for square. And we got plus y squared is equal to, what did we say, 1. That's what it looks like right here. And so notice once again, this vertical line that we've already got set up, it's going to be intersecting all over the place in more than one spot. So we've got a positive root, negative root going on. No, it's not a function. All right, so that's how we're going to tackle algebraically solving to see if it's a function or not. The main thing you're looking for, and a lot of times it comes up when you're taking that square root of both sides, you're getting a positive root and a negative root. I didn't have it really planned. Let's look at one more because this is going to come up too. So let me just kind of write this out here. Sometimes we get something like this. Y equals the square root of x plus 2. Now, up here, we put in a positive or negative because we went from this step right here to this step. We introduced the radical, so we had to put a plus or minus in front of it. Here, this was the original problem. The author is saying y equals square root of x plus 2, is that a function or not? If they wanted you to include the negative root, they would have put a negative there. But they didn't. They just wrote it as basically square root, which we're going to say is the principal root or just the positive roots. So this is, yes, a function because we only want to take the positive root. We only put that plus or minus there if the original problem already had it in it, or if we're taking the square root of both sides. In fact, if we go back to Desmos real fast, if we change this up here to that function, y equals the square root of x plus 2, notice it passes the vertical line tests. See that? It's just our square root function and it's shifted to the left twice. So that is a function. Now, if it were plus or minus, let's see if we can put a plus or minus in front of it. Sometimes these keys are in here. Let's look. I don't see it, but if we put in, let's see, another function here. Let's say if it were y equals the negative square root of x plus 2, that would be the plus or minus deal here. I'll make it in the same color. I think I can make it the same color. There we go. This would be closer to if we had plus or minus in front of it. Notice it intersects twice, but the original problem did not say plus or minus. We didn't introduce the radical, so it's a yes, all right, because it started off as square root of x plus 2 from the get-go. All right, let's take a look at our next section here, and that's on function notation. So we've done a lot of y equals, like for instance in this case, y equals 3x minus 5. And now we're going to revisit this thing right here, our functional notation. So this is just a different way to write this up here. In fact, it may seem confusing at first, but as you progress through mathematics, it makes life so much easier. So in this case, we use the letter F. You can later on use different letters like G. Sometimes we use H. Different letters are used at different times. But it's just another way to name our functions. So we're going to see here in a moment, we're going to have this problem with an f of x and the g of x. And it's nice and easy for me to tell you, look at the g of x, and you know I'm talking about this function. I don't have to say x plus 2 quantity squared. I can say, look at the f of x, and you know I'm talking about the one on the left. If we have 5 different functions, we might have like the f of x, the g of x, the h of x, the s of x, the t of x, all those things listed out there. So it's convenient because we can name it. Another convenience is I don't have to say plug in 2 and then plug in negative 4. It sounds silly. I can just write in 2 and negative 4 in the parentheses, and that means substitute in 2 into the function and evaluate it. All that right there is condensed into that notation right there. Now, in the beginning, it's real tempting just to put in 2 into the function, 3 times 2 minus 5, and give me the answer. But I want you to get into this habit right here. Whenever you're evaluating a function with what's inside the parentheses here, make sure you got the right function. Okay, it's the f function. And then everywhere you see an x, put a set of parentheses. So rewrite the function with the parentheses in place of the variable. And then substitute in this right here. Okay? And that will keep you from making a ton of mistakes when stuff gets harder. So I'm going to put the 2 in right there. And now I can evaluate. Remember to use the order of operations. 3 times 2 is 6. 6 minus 5 is 1. So we can say that the f of 2 is equal to 1. All right, try the next one. The f of negative 4. So once again, I'm going to rewrite the function, and everywhere I see an x up there, I'm going to put a set of parentheses, and then I'm going to substitute in what I'm supposed to be substituting in, and evaluate using order of operations. So this becomes negative 12 minus 5, which equals negative 17. So once again, we can say that the f of negative 4 is equal to negative 17. All right, let's look at number 16 here. So now we know, okay, we're using the g function that's defined up here, x plus 2 quantity squared, and we want to evaluate it when x is equal to 1. So we're going to say we've got parentheses plus 2 quantity squared, put a 1 in, and then we can evaluate using order of operations. 1 plus 2 is 3, and 3 squared is 9. So the g of 1 equals 9. Number 17, f function. So we've got something squared minus 1, put the 3 in. 9 minus 1, which is 8. So the f of 3 is equal to 8. Back to the g function. So everywhere I see an x, put a set of parentheses. Negative 2 goes in. Negative 2 plus 2 is 0, and 0 squared is 0. And then one more here, the f of negative 2. So I'm going to rewrite this, the f function with a set of parentheses in place of the x. And then everywhere I see that parentheses, put a negative 2 in. Squared, I get 4, and 4 minus 1 is 3. So the f of negative 2 equals 3. So hopefully you've seen that before, and hopefully you're trying out with my method of putting the parentheses in, because as this gets more and more complicated, you're going to need that method down. So let's look at another one. So this one right here says the g of x is equal to negative x squared plus 4x plus 1. Now we're getting to some fun stuff, right? So let's see. Let's write this out. Negative parentheses squared plus 4 times parentheses plus 1. And everywhere I see a parentheses, I'm going to put a 2 in its place. Follow the order of operations. This says to square it first and then multiply by negative 1. If we wanted to, say, square the negative 2, we would wrap this. It'd be negative x squared. So square the 2 first, and you get 4. Then multiply by negative 1, you get negative 4. Plus 8 plus 1. And this gives us 5. So the g of 2 is equal to 5. I'm going to write this just a little bit below because it's hard. I guess I didn't leave myself enough room. So now we want the g of t. So once again, everywhere I see an x, I'm going to put a set of parentheses. So I get negative x squared plus, well, not negative x squared, it's just an empty set of parentheses, plus 4 times parentheses plus 1. And everywhere I see a parentheses, I'm going to put a t in its place. Not a whole lot I can go from there. So the g of t is equal to negative t squared plus 4t plus 1. Couple of things here. One, you say, well, that didn't really change much. It's just getting us used to saying we can put a variable in for x, or we can put a variable, or we can put in a whole function in for x and evaluate it. But this is getting us to that point. The other thing to note is I do my t's like that. They look like weird little headless stick figures, but that's because it doesn't get confused with a plus sign, okay? Let's look at the h of x equals x plus 4. So they want us to evaluate x plus 1. Now be careful with this. This is where a lot of students will mess up, okay? So everywhere I see an x, I'm going to put a set of parentheses. And then I'm going to substitute x plus 1 in there. And in this case, this simplifies to x plus 5. And maybe if you pause the video and try that out ahead of time, you got that right. But, you know, a lot of times students will just add 1 to the end of this, and that's not the correct way. In this case, it works out to be correct. But get in the habit of putting that parentheses down first. Try out number 22. Pause the video and give it. All right, remember what we're going to do. We're going to say, everywhere I see an x, I'm going to put a set of parentheses. So I rewrote this function, and where I saw an x, I put a parentheses there. And what we're going to do is, in that parentheses, we are substituting in x plus 2. So x plus 2 goes in that parentheses. So basically, we're replacing this variable with what's ever written right here. In this case, it just happens to be another x in there. Follow along with me so you make sure you get this one right. This is the real tricky one. So from here, I can multiply out this binomial. Remember our trick for taking a binomial square. We square the first term. We take the product of the two, 2 times x, and then double it. You get 4x, and square the last term, 4. So this right here became this trinomial. And then don't forget to bring down this plus 1. And now I can say, hey, 4 and 1, they're common terms. So we can, or like terms, we can say 4 plus 1 is 5, and we get x squared plus 4x plus 5. And so this is what the g of x plus 2 is equal to. All right. Let's look at another one here. Now, this is what we call a piecewise function. So we're at x squared plus 1 when x is less than 0. And when it's equal to 0 or greater than that, it's the linear function x minus 1. So in this case, this is where we got to look at first. So when I want to evaluate negative 1 here, which category does it fall under? Is negative 1 less than 0 or greater than or equal to 0? Well, it's less than 0. So this is the function I'm going to use. So I'm going to say something squared plus 1, and then substitute negative 1 into it. Negative 1 squared is 1, and 1 plus 1 is 2. So the f of negative 1 equals 2. Now we've got, for letter B here, the f of 0. So looking up here, I'm going to use the bottom one because this says x can be bigger than 0 or equal to 0. This one doesn't include 0, so it's going to be something minus 1. Put this in for it. And 0 minus 1 is negative 1. So the f of 0 equals negative 1. All right, one more here, and that is the f of 1. So looking up top, anything bigger than 0, I'm going to use the bottom function. So I'm going to use something minus 1. And in that something, I'm going to put 1. So 1 minus 1 is 0. And so the f of 1 equals 0. And that's how we work a piecewise function when we're using function notation to evaluate x values. Okay? So we did a couple things there. We learned what a function was, how to determine if a relation was a function. And then we learned about functional notation and evaluating those functions using functional notation. So try out the examples. Let me know if you have any questions. And thanks for watching. Thanks for working hard.